This is my circuitry assessment. It's going to focus on using the loop rule and node rule to find the electric field and electron currents for multiple bulbs in a circuit. For the circuit shown below, A, determine the number of paths in the circuit, each involving a round trip that begins and ends at the same location. B, use the loop rule to determine the energy conservation equation for each path, where E refers to the electric field in the bulb and L refers to the length of the bulb filament. Assume the electric field in the wire is small enough to neglect. C, using the node rule, write the charge conservation equation for the circuit. And D, if the battery has an EMF of 1.5 volts and the length of the tungsten filament in each bulb is 0.008 meters, use the given properties for the filament and any valid energy conservation and charge conservation equations to solve for E1, E2, I1, and I2. For part A, a round-trip path begins and ends at the same location, such that each path goes through a wire, a bulb, or a battery. The three possible paths in the circuit are path 1, starting at point 0, going to point 1, through bulb 1, to bulb 2, to point 2, to point 4, back to point 0, and for path 2, starting at point 0, to point 1, to bulb 1, to bulb 3, to point 3, to point 4, and back to point 0. And for path 3, starting at point 2 to point 3, through bulb 3, to bulb 2, and then back to point 2. In a round trip, the change in potential is always equal to 0. For path 1, the energy conservation equation is 2 EMF because there's 2 batteries, minus the electric field of bulb 1 times the length L, minus the electric field of bulb 2 times the length L is equal to 0. For path 2, the energy conservation equation is 2 EMF minus E1 times L minus E3 times L is equal to 0. For the third path, the energy conservation equation is E2 times L minus E3 times L is equal to 0. For part C, write the charge conservation equation using the node rule. According to the node rule, in the steady state, the current entering a node is the same as the current exiting that node. In this case, I1 is equal to the current through bulb 1, I2 is the current through bulb 2, and I3 is the current through bulb 3. Therefore, the charge conservation equation is I1 is equal to I2 plus I3. For part D, solve for the electric field and electron currents for bulb 1 and bulb 2, using the energy and charge conservation equations and the given property values for the tungsten filament inside the bulb. The expression for the resistance of the tungsten filament in each bulb is given by big R is equal to the specific resistance of the tungsten times the length divided by pi r squared. The resistivity of the tungsten is given by rho is equal to 1 over q times mu times n, where q is the charge of an electron, mu is the electron mobility, and n is the electron density. Plugging in the given values for mu and n, we get that the resistivity of the tungsten filament in each bulb is 5.78 times 10 to the negative 8 ohms times meter. Now plug in that calculated value for the resistivity of the filament into the equation for the resistance. We get that R is equal to 5.78 times 10 to the negative 8 times 0.008 meters divided by pi times 5 times 10 to the 6th squared. And we get that the resistance is equal to 5.89 ohms. For path 2, bulbs 2 and 3 are identical and connected in parallel, so they carry equal currents and potential differences. From the charge conservation equation, I1 equals I2 plus I3. Knowing that bulb 2 and bulb 3 are identical, it is clear that I1 is twice that of I2. So the potential difference of bulb 1 is twice that of bulb 2 and 3. Since E1 is equal to 2 times E2, we can substitute 2E2 into the energy conservation equation. So E2 is equal to 2 EMF divided by 3L, and E2 is equal to 125 volts per meter. Now substitute the value 125 volts per meter for E2 into the equation for E1 equals 2E2. E1 is equal to 250 volts per meter. The expression for the electron current through bulb 1 is I1 is equal to E1 times L divided by R. Plugging in the values for E1, L, and R, we get that I is equal to 0.34 coulombs per second. Multiplying that value by the electron density of the filament, we get that I1 is equal to 2.1 125 times 10 to the 18th electrons per second. Since I2 is equal to half of I1, we can easily solve for I2 by dividing the value of I1 by 2. So we end up getting that I2 is equal to 1.0625 times 10 to the 18th electrons per second.